Every morning, 60 million people across the Tokyo-Nagoya-Osaka corridor do the same math. 90 minutes on the Shinkansen, or 2 hours and 20 minutes if you want Osaka. That math is about to become obsolete. Japan is building something beneath its mountains that most of the world still hasn't fully processed. Not just a fast train, a machine that floats, has no wheels, touches nothing, and moves at the speed of a fighter jet on approach. And right now, deep under the Japanese Alps, the biggest tunnel boring operation in that country's history is carving the path for it. Here's what makes this different from every other infrastructure story you've heard. The technology has been ready for years. The machine exists. It has already broken the world speed record. The only thing standing between this and operational service is rock, time, and one stubborn prefecture. And that part of the story is the part nobody talks about. Stay for that. Let's start where Japan always starts. Not with a ribbon cutting, not with a press conference. With a quiet decision made 50 years before anyone is supposed to notice. In 1962, Japanese engineers asked a question that sounded absurd at the time. What if a train didn't need rails at all? Not in the sense of hovering science fiction, but in the literal engineering sense. What if you suspended a vehicle inside a magnetic field, eliminated every point of physical contact with the ground, and let it fly through a tube at whatever speed the power supply could push it to? That question became a research program. The research program became a prototype. The prototype became the Chuo Shinkansen. And the Chuo Shinkansen is now one of the most expensive infrastructure projects on the planet, with costs that have climbed to over 11 trillion yen. That is roughly $61 billion. For context, that is more than the entire annual GDP of Bolivia. For a single rail line. But here's the twist. That number is not the remarkable part. The remarkable part is what the machine actually does. Japan's L0 series maglev train holds the world speed record for any crewed rail vehicle ever built. 603 kilometers per hour. To put that in your body, not just your brain, a standard Shinkansen bullet train already moves fast enough that the countryside outside the window dissolves into a smear. The L0 moves nearly twice as fast. At that test speed, it would cover the entire distance between central Tokyo and Nagoya in under 30 minutes. The planned commercial operating speed is 500 kilometers per hour, which still makes the current Shinkansen look like a commuter bus. Tokyo to Nagoya in 40 minutes. Tokyo to Osaka in 67. Here is the part almost nobody talks about. This train does not touch the track. There is no wheel. There is no friction. Superconducting magnets in the train's bogies create a repulsion field so powerful that the entire vehicle lifts off the guideway and floats, suspended in a U-shaped channel, propelled by alternating magnetic pulses that the passenger does not feel. The train doesn't roar. It hisses. At 600 kilometers per hour, it hisses. That is the sound of 50 years of engineering working exactly as intended. And the tunnel boring machine they just assembled at the Kanagawa station site is built to dig the path for this thing. That machine. Let's talk about that machine. The shield boring machine assembled at the Chuo Shinkansen's Kanagawa construction site is 14 meters in diameter. Picture the cross-section of a 5-story building. Now imagine that cross-section is a spinning cutting head made of hardened steel teeth, and it is being pushed forward through mountain rock by hydraulic jacks, generating thousands of tons of force. The assembly alone, which began in June of 2025, took months to complete. Once it moves, it will carve roughly 3.6 kilometers toward Nagoya in this phase alone. And this is just one machine, on one segment, of a line where 90% of the entire route is underground. 90% tunnels, 240 kilometers of the 286-kilometer Tokyo-Nagoya section runs through the earth. The deepest point sits 1,400 meters below the surface. That is nearly a mile straight down. For comparison, the Channel Tunnel between England and France, one of the most famous engineering feats in modern history, sits about 75 meters below sea level at its deepest. Japan is digging 20 times deeper than that, through active seismic zones, under the Japanese Alps, in a country that sits on 4 tectonic plates and experiences more earthquakes per year than almost anywhere on Earth. And it gets crazier. The reason 90% of the route is underground is not just geology. It is physics. To run at 500 kilometers per hour, you need a nearly straight line. Any curve tighter than a specific radius creates centrifugal forces that no magnet can fully compensate. The Japanese Alps do not cooperate with straight lines, so the engineers went under them. They designed a route that punches directly through the mountain range, trading surface complexity for underground depth, and accepted that this would be the most expensive per-kilometer tunneling project in Japan's history. Those tunneling costs are a key reason the price tag ballooned from the original projection of 5.5 trillion yen to over 11 trillion. The new figure is more than double the initial estimate. JR Central, the railway company building the line, acknowledged the revised costs at a press conference in Nagoya in October of 2025, with the company's president describing the scale of the increase as something to be taken seriously. Bond issuances are already in the pipeline. The Japanese government has extended a loan of 3 trillion yen to keep the Osaka extension on schedule, targeting completion as early as 2037 instead of the previously projected 2045. That is the arc of this project in one sentence. The cost doubles, the government steps in, and the timeline actually gets shorter for the extension. Japan does not slow down because it gets expensive. It writes a bigger check and keeps going. But the delay story deserves its own moment, because it is the strangest part of all this. The biggest obstacle to the world's most advanced train was not a mountain. It was 9 kilometers of tunnel in a single prefecture. Shizuoka Prefecture refused to grant construction approval for a short section of the line, citing concerns about the impact of excavation on the Oi River water table. A 9-kilometer gap in a 286-kilometer line held the entire project back for years. The original 2027 opening between Tokyo and Nagoya is no longer possible. The current target is no earlier than 2035. A compensation agreement with Shizuoka was finally concluded in January 2026, raising expectations that the Shizuoka section will move forward within the year. One prefecture, 9 kilometers. 8 years of delay on a $90 billion project. If you want to understand why megaprojects cost what they cost, it is rarely the mountain. It is usually the 9-kilometer conversation nobody expected to have. Meanwhile, the technology itself is not sitting still while the lawyers and local governments negotiate. In February 2025, JR Central announced the M10, an updated maglev design that represents the next generation beyond the L0 prototype that set the speed record. The M10 introduces what engineers call riblet film on the exterior. The concept is borrowed directly from shark skin. Sharks, over hundreds of millions of years, evolved a surface texture of microscopic ridges that reduce drag by disrupting the thin layer of turbulent airflow closest to the skin. Japan applied that same principle to a train moving at 500 kilometers per hour through a mountain tunnel. The riblet film cuts aerodynamic drag. Less drag means less energy consumed. Less energy consumed means the train's operating economics become viable at commercial scale. The M10 also uses high-temperature superconductors. Previous generations required the magnets to be cooled to within a few degrees of absolute zero using liquid helium, a process that added mechanical complexity, weight, and maintenance cost. High-temperature superconductors operate at warmer conditions, which simplifies the refrigeration equipment significantly. Less weight, lower energy draw, simpler maintenance. A single M10 intermediate car began testing in July 2025. Not a full train yet. One car. Because that is how Japan does it. One car, 10,000 test runs, 6 billion data points, then a full formation. The Yamanashi maglev test line, where all of this testing happens, is 42.8 kilometers long and runs test operations daily. It is the most active maglev testing facility in the world, and it has accumulated over 2 million miles of test running since 1997. That is enough distance to circle the Earth roughly 80 times. Now, zoom out to the geopolitical frame, because this is where the scale of what Japan is building becomes fully clear. The combined metropolitan area of Tokyo, Nagoya, and Osaka holds roughly 60 million people and generates more than 60% of Japan's total GDP. Right now, moving between those three cities by the fastest available train takes between 40 minutes and 2.5 hours, depending on your origin and destination. When the Chuo Shinkansen opens, Tokyo to Nagoya becomes 40 minutes, and Tokyo to Osaka becomes 67. Those three cities, effectively, merge into a single economic zone. The commuting radius expands. The labor market homogenizes. Land values redistribute. Industries that today cluster in one city because proximity matters find themselves with access to the full talent pool of all three simultaneously. One rail line does not just move passengers faster. It restructures where 60 million people can live, work, and invest. And the countries paying attention to this are not just Japan's neighbors. China operates a commercial maglev line in Shanghai with a top speed of 431 km per hour. China's own next-generation maglev prototype has been reported targeting 600 km per hour in testing. The speed gap between Japan's technology and China's is narrowing. JR Central has long been positioning the SC maglev system for export, pitching it to potential buyers, including development partners in Australia, where a consortium was formed to explore linking Sydney, Canberra, and Melbourne. The Northeast Maglev project in the United States, which would have brought Japan's technology to the Washington, D.C. to Baltimore corridor, was formally cancelled by the Federal Railroad Administration in late 2025. That decision ended a project that had been in development for years and leaves the United States without a credible path to maglev rail in the foreseeable future. Japan is not building a fast train. Japan is building a template. The question of whether superconducting maglev becomes the global standard for 21st century intercity rail depends almost entirely on whether the Chuo Shinkansen opens on budget, on schedule, and runs without incident for its first decade of commercial operation. Every government watching this project knows that. So does every competitor. That is the real machine no one saw coming. Not the 14-meter boring head cutting through the Alps, not the L0 doing 600 km per hour in a mountain test tube. The real machine is the entire system. The 50 years of institutional patience, the willingness to double the budget without abandoning the project, the shark skin physics applied to a train, the boring machine assembled bolt by bolt 6 stories underground. A machine built not to impress, but to endure. If you want to see what the rest of the world is building next, this is the place to be.